In a previous lecture, we spoke about the concept of magnetic fields, and we said that any object called a magnet will in fact produce a magnetic field. Now, we left off by saying that there is a relationship between electric fields and magnetic fields. In other words, these two concepts, very different concepts, are somehow interconnected. Now, in this lecture, we will explore what this relationship is between electric fields and magnetic fields. So to begin, let's recall what a stationary charge is. A stationary charge Q can be either negative or positive, and stationary simply means that our charge is not moving, it's not in motion, it's stationary, it's staying in one place. Now, from experiments, we know that a stationary charge will produce an electric field, but it will not produce a magnetic field. On the contrary, if we take our charge, same charge, and it begins to move, so we create a current in the opposite direction of motion, we will create not only a changing electric field, but a magnetic field. In other words, a changing electric field will produce a magnetic field. So for example, let's look at the following illustration. Suppose we take a very, very long wire, much longer than drawn on this board, and we allow our electrons to flow from this end to this end. So that means because electrons are flowing in this direction, our current must be going in the opposite direction by convention. So our current is going from this way all the way this way. Now that means since our electrons are moving and our electric field is changing, that means that our magnetic field must be created. So the magnetic field created by the movement of electrons in a very long wire looks like concentric circles. So if you slice this guy open and look at the cross-sectional area of our wire, if our current is coming out of the board and our electrons are going in, then our magnetic field will look like concentric circles going around our cross-sectional area of the wire. Now, my question is, in which direction is our magnetic field pointing? Recall that magnetic fields, like electric fields and gravitational fields, are vectors, and that means that they have both magnitude and direction. So we have to use something called the right-hand rule, and this right-hand rule will tell us the direction of our magnetic fields. So the way we use or apply our right-hand rule is in the following manner. We take our right hand and we grab our wire. Now we point our thumb in the direction of our current, not the electrons, but our current. So since our current is going this way, we grab the wire like so, because our thumb points in direction the same as the current. If we took it this way, this would point in direction of electrons, but we want to grab it this way because our thumb should point in the same direction as our current. So if we grab it this way, these fingers curl in the direction of our electric field, and that means they curl this way, so our magnetic field points in this direction. At this point in time, it's pointing up. At this point, it's pointing into the page. At that point, it's pointing down, and at this point, it's pointing out of the page. So once again, if we slice this guy and take the cross-sectional area, we see that since our current is going this way, our magnetic field must be going like this. So at this pointing, it's pointing up. At this point, it's pointing sideways. At this point, it's pointing down, and at this point, it's pointing this way. Now let's look at the equation that allows us to find our magnetic field at a point close to our long wire. In other words, suppose we had the same long wire and we had electrons flowing. Now these electrons, these flowing electrons, will create a magnetic field. And if we place another charge, say a distance r away, that charge will feel a magnetic field, or that object will feel a magnetic field. To find the magnetic field felt by that object a distance r away, we have to use the following formula. So our magnetic field is represented by the capital letter B, and it's a vector, so that means I draw my arrow on top. Now, so our magnetic field, which is by the way given in units known as Teslas, or Tesla, capital T, equals, this guy is simply a constant. So mu over 2 pi, or mu naught, Mu naught is known as the permeability of free space, and it has the value of 4 pi times 10 to the negative 7 teslas times meters divided by amperes. Now 2 pi is simply 2 times 3.14 and so on. I is our current in amperes, and R is our distance in meters. So if we want to find how much a certain object feels, or what the magnetic field on an object is a distance r away from our long wire, assuming that our distance is much shorter than the length of the wire, we can find it by using this formula. So let's do an example. So let's do a really quick calculation using our formula. Let's look at the following illustration. Suppose we have a very long wire that's much longer than our distance between some point. And suppose this point is 15 centimeters away from my wire. And we're assuming that this distance is much smaller than the distance or the length of my wire. So that means we can apply this formula. And this formula states that our magnetic field at this point away from our wire that has a current of 25 amps going up can be given by mu naught divided by 2 pi times I divided by R, where I is our current in our wire, R is our distance between the point and the wire, and mu naught over 2 pi is simply a constant. So mu naught is 4 pi times 10 to the negative 7 teslas times meters divided by amps. So that means since we have meters, we must convert this to meters first. To convert this guy to meters, we divide 15 by 100 and we get 0.15 meters. So plug in 25 into I, plug in 0.15 into our R, plug in the mu naught constant, and we get, after plugging stuff into our calculator, our answer to be 3.33 times 10 to the negative 5 teslas. This is the electric or magnetic field felt at this point, at point 15 centimeters away from a current of 25 amps going along a very long wire.